So unmanned aerial vehicles, we've been working on this for about 15 years now, and I want to show you this picture which illustrates the number of unmanned aerial vehicles and how it's grown over the years. So this is a picture in 2010, and the smaller vehicles that I'm going to talk to you about, we started playing around with these in 2005. And you could see this exponential growth in these vehicles. In 1980s, we did not have commercial GPS. And therefore, it was really hard to develop autonomous flying robots. So in 2010, people said, well, this is going to be a $10 billion industry, and people projected all kinds of uses, but it was primarily military uses. It was about surveillance, about spying, force protection, warfare, all the kinds of things that many of us are not really interested in. Certainly from a scientific standpoint, these don't present the challenges or the potential for impact, no pun on that word. So the FAA famously predicted that we'll have 15,000 civilian drones by 2020. So fast forward for 5 years, and now they're all over the place. Right? I don't have to explain to anyone what an unmanned aerial vehicle is, what a drone is. And going back to the number of 15,000 drones were sold in a single month last year, per month, and people estimate that over 1 million drones were sold just in December during the Christmas season. So it's a $15 billion industry already, and again, people make famous predictions, it's going to grow to 20 billion, and you know that 25 billion by 2020, and you know that that number is also going to be wrong. But what's exciting now is that the applications have grown to areas that we never imagined. So agriculture, inspecting different aspects of our civilian infrastructure, border patrols, photography, and construction, and so on and so forth. So it's really grown to be a very exciting field. Of course, different people call them different things, and so we prefer to use the word aerial robots because robots we think of as being smart, able to take their own decisions, and so on. The military calls them remotely piloted vehicles because, in fact, they're not drones. There are human beings that are controlling these vehicles every step of the way. So it's actually a misnomer to call them drones. But of course, the popular press and all of us call them drones. And so to me, they're all now pretty much the same thing. And it seemed appropriate to show this picture in this museum. You think about the evolution of aerial robots, and we are just starting. And really, we want to be further along. And in my lab, we look at what I call the 5 S's of aerial robotics. So the first S is we want to make them small. And if you want to navigate in environments with humans, you want to be small, you want to be able to maneuver, you want to go through doorways, you want to go across rubbles in buildings. And so we are looking for making them small. We also want to make them safe. Clearly, we don't want something banging into humans, causing harm. And so therefore, we're trying to make them as safe as possible. Smart, this is an obvious thing. If you're building a robot, you want it to be smart. We also want these robots to move quickly. So we want to create robots that you actually have to slow them down to actually see what happens, just like NFL replays. So those are the kinds of robots we're shooting for. And then finally, we think about swarms. So that's the 5th S in our vernacular. So having just given you a flavor of the kinds of problems we're interested in, I want to tell you a little bit about how we think about autonomous control. So first, you're trying to control something which really lives in 6 dimensions. There's 3 positions and 3 orientations that you have to simultaneously control. And a robot like this has 4 rotors, and you only have 4 inputs. You have 4 motors, and you're trying to control, with these 4 motors, 6 different things. And the system is underactuated. It's sort of an unfair problem mathematically because you're trying to do 6 things with only 4 inputs. So these robots are called quadrotors because they have 4 rotors. Even if you add more rotors, you're fundamentally underactuated. And so we spend a lot of time just attacking this problem. The second thing we do is think about how to design software that runs in real time. So I'm showing you a picture here. I'm just trying to impress you with a block diagram. But the thing I want to get to you is the fact that you have these feedback loops. So if you look at the innermost feedback loop, you'll see that it operates at roughly a millisecond. That means every millisecond, the robot is estimating its rotation, its attitude in the real world, its angular velocity, and trying to regulate that to get the precise orientation it wants. So then the intermediate feedback loop in the middle, you're feeding back position and velocity, and that operates roughly at 10 milliseconds. And then finally, the outermost loop, you're thinking about trajectories in the real world and how to plan trajectories, and that operates roughly at 100 milliseconds. So those are the three levels of intelligence that need to be built into the system. And although all our students are engineers, they spend 80% of the time thinking about software. And so therefore, they're also become computer scientists in this field. The most critical things are the computations that happen on board. So these are the orientation calculations to figure out how to control the orientation. Some of the other computations actually don't happen to happen on board. So if you look at the position, sometimes we get estimates of positions from external cameras, and those computations can actually happen off-board. In fact, a lot of the trajectory planning software that we write and test in the lab happens on a laptop like mine. So today we hear a lot about cloud infrastructure. Well, we use the cloud infrastructure to run real-time control loops for vehicles like this as they maneuver through the environment. We try to make these robots as small as possible. This is work of Yash Mulgaonkar. This is the smallest robot we've built. It's only 11 centimeters tip to tip, has a max speed of about 6 meters per second. And in terms of the size and the velocity, in terms of body lengths per second, it is equivalent to a Boeing 787 flying 50 times the speed of sound. So it actually flies pretty fast for something this small. By making it small, we automatically make it safe. And by making it small, we also make it more maneuverable, as I'll explain in a minute. So the inspiration for this really comes from nature. So if you look at honeybees, for example, they're extremely small, they're very maneuverable. In fact, unlike all the big robots we build, they don't even think about avoiding collisions. So for us, the nightmare is we build these big behemoths, and the first thing we think about is we don't want to bump into other features in the environment, bump into each other. Well, you look at these honeybees, and they love collisions, because by colliding, they learn. So by contacting your neighbor, you actually know where your neighbor is, and you know a little bit about your environment. So we'd love to be able to create robots at this scale. So in our lab, we actually think about how to scale things down. So here you see work of Yash Mulgaonkar, and that's the sound of the robots. You could see that one of the things you'll notice is that when the robots become small, they're able to respond more quickly to perturbations. In fact, we can show through scaling laws that the maximum acceleration you can get goes as 1 over the characteristic length. In other words, you make a robot half the size, and the ability to maneuver in the rotational direction doubles. Likewise, the robustness, which we call the basin of attraction, grows dramatically as you shrink the size of the vehicle. So this might be counterintuitive. So all of us who fly on large aircrafts prefer those to smaller turboprops. But the turboprops or the large aircrafts are never subject to perturbations like this. If you want to respond to collisions and react to them and be robust to them, you really want to think about sizing things that are much smaller, and that's what we try to do. Anecdotally, when we first started working on this, we realized we needed to have a first aid kit, so we started buying Band-Aids and things like that. And if you plot a histogram of Band-Aids over the years, now it's tailed off. When we move to these little guys, people don't get hurt, which is great. And this is, again, 1/20th speed, probably the first mid-air collision, planned mid-air collision, and vehicles bumping into each other and recovering from these collisions. These robots are traveling at roughly 2 meters per second, walking speed. So imagine one person standing still, and you walk right into that person. You feel the impact. Well, these robots feel it, but they're able to recover from it quite spontaneously. So that's the advantage of size. And in terms of figuring out how to plan these motions, we think a lot about how to represent the dynamics of these vehicles. So if you look on the right-hand side, there's this huge vector of things that the robot stores. Its position, its velocity, its rotation, its angular velocity. And we think of clever ways in which to abstract from this a smaller dimensional representation, which consists only of the position and the orientation, the heading angle, much like you would when you drive a car. When you drive a car, you think of the position in the road, and you think of the yaw angle of the car, and that's roughly what you see on this left-hand side picture. If you work in this smaller abstraction, then you can think about planning trajectories in that space that are safe, and then some fancy mathematics that ensures that these trajectories are as smooth as possible. So again, the intuition is if you have lots of inertia, you don't want your trajectories to be jerky. You want them to be smooth. So we try to minimize what is called the snap, which is the fourth derivative of position over time. So the first derivative is velocity, second is acceleration, third is jerk, fourth is snap. You can also do crackle and pop, but we don't. But we try to minimize that and then find the right trajectory. So that's the essence of the planning problem. So once you do that in this simpler space, which is a problem in computational geometry, then we transform this over into this more complex space, and then we execute them. And that's basically what you see in these videos. You see the robot going through these planned obstacles. So if the robot knows where the obstacles are, it can plan these minimum snap trajectories at a fraction of a second, often 20, 30 times a second. And it doesn't matter if the obstacle is moving. If the robot knows how the obstacle is moving, it can determine how to plan trajectories to go through the obstacle. Some of you may have seen videos of birds fishing to catch their prey, and this is amazing. You look at this bird coordinating its flight, its vision, and so on, and its claws, and we try to do the same thing with robots. And so here's a robot fishing for Philly cheesesteak hoagies, and it's able to pick that out. So again, we focus on the split-second timing, coordinating vision, coordinating arms, coordinating hands, and flight as you fly through complex environments. And then finally, work of Sarah Tang, where she's able to use this framework to think about transporting suspended payloads whose length is more than the height of the window. So you have to figure out how to get the momentum of the object to be such that the suspended payload swings through first before the robot actually goes through it. So these calculations look complicated, but by abstracting the dynamics to the simpler space, we're able to solve this in real time and then feed it to the robot. And then lastly, this problem of trying to perch in complex environments. Again, you want to perch to save energy, to rest. And the challenge for us is to perch on vertical surfaces. So we have a gripper, which is made out of a dry adhesive. I call these like the Spider-Man claws, and they're able to hold on to flat surfaces, a gripper designed by colleagues at Stanford in Mark Kutkowski's lab. And again, this framework allows us to land on any vertical surface, or any tilted surface for that matter, at just the right velocity to achieve perching. So we're able to get autonomy in a wide variety of settings, not just in flight, but also perching, grasping, and things of that nature. I want to tell you a little bit about the problem of state estimation. And everything I've shown you thus far, we have cheated. We have cheated in the following way. In the lab, our robots are equipped with motion capture cameras and reflective markers. So the cameras see the reflective markers, and they compute the position of the robot 100 to 200 times a second, and then deliver that information to the robot. So the robot knows where it is at all times. So this gives the robots an unfair advantage, and they're able to do all the things that you just saw with amazing precision. So in the real world, and here's a typical building on the Penn campus, it becomes really challenging. Without external cameras, you don't know where you are. In fact, in this building, GPS doesn't work, my cell phone doesn't work, we barely get Wi-Fi coverage. So how do you get robots to localize in complex environments like this? So we work a lot on this problem, and I want to show you a prototype that was built by a former student who's now a professor at Hong Kong University of Science and Technology, Xiaoji Shen. And the system he built consists of two forward-facing cameras, and you can see the GPS receiver on top. You can see a laser scanner, which is this orange band on the top. And then there's a downward-facing camera, too, which you don't see. So this package allows the vehicle to sense features in the environment and determine where it is relative to those features. And then as it moves, much like humans, when we walk, we're looking at things in the environment, we take steps, we know roughly how far we've walked, and then we look at how these features are flying past our retina. We integrate that motion to then figure out where we are in the real world. And that's what this robot is able to do. And here you'll see work of Sikong Liu that essentially takes this information coming from the robots and is able to construct these three-dimensional maps. And this is just outside our lab. You can see it build high-resolution maps at 5-centimeter resolution. And now it's entering the lab, as you can see, with all the clutter that obviously our lab. And the bottom, you see the map that it's building. And you'll see that the color of the objects that it sees is overlaid on this map. So this is now leading to quote-unquote smart. And it's not really smart in the sense that it's not making any intelligent decisions in this particular experiment, but it's smart enough now that it's able to perceive the environment and represent it in terms of this three-dimensional map, which is a great starting point. And imagine being outside a building and then deploying the vehicle inside the building. Well, you have a complete picture of what's inside the building. You know something about its structural integrity. If there's an active shooter in the building, you can probably detect that shooter. And if there are victims in the building, you can localize and tell rescue workers where they are. So this basic technology, while it might not appear to be very smart to us, is actually smart enough to do lots of useful things. Here's the same type of technology in outdoor flight. Many of us have now heard about Amazon and Google wanting to deliver packages to our doorstep. This, in theory, works. It works when you're flying at, let's say, 400 feet, just at the FAA ceiling, where GPS is clear and you're relatively unobstructed. But what happens when you get to features such as trees, where your GPS might not work, and in our case, when you have cameras, the cameras might not have enough illumination to function. So we look at combinations of sensors, as you see on the top left. And at every instant, the robot is able to estimate its error. So if you see that ellipsoid in the middle, this is not unlike the ellipsoid you see in your Google Maps, which tells you the error in your position. So the vehicle not only calculates where it is, it's also able to tell the software what its estimate of the error is. And as it goes around this complex, indoor and outdoor, using lasers indoors where cameras and GPS don't work, and outdoors in bright sunlight where the cameras doesn't work, but maybe GPS works, it's able to navigate its way through a fairly complex environment. So this is a 0.5 kilometer flight at roughly walking speed, and it's able to do all of this autonomously. So this is a very important technology as you sort of get to close to human built environments, like with buildings or trees that just happen to grow since the last time you were there. So you need to detect that, you have to react to it, and then behave in a safe way. So one problem we run into is that these vehicles burn a lot of power. So if you look at rotorcrafts, they burn roughly 200 watts per kilo. So that's a lot. That's like 4 light bulbs for every kilo of payload you carry. And part of the problem is that all this hardware I've shown you is actually quite heavy. So the cameras are about 80 grams. The laser rangefinder that I showed you is about 370 grams. Our Intel processor, the board, is about 200 grams. So you add all of this up, not only are you burning power to power the devices, you're also burning power just to carry these devices. And so a big challenge for us is actually to limit the power consumption. If you don't limit the power consumption, you have to carry bigger batteries. And you carry bigger batteries, that's extra payload, and you're burning even more power. And all the things I've been telling you about being small, being safe, that goes right out the window because your devices keep getting bigger. So this is a big challenge for us. But consumer electronics sometimes comes to the rescue. So if you ask yourself the question, what is an inexpensive device that you can buy today that has sensing, computing in a lightweight package and low power? Of course, it's your smartphone. So we started asking the question, could we build something that's powered exclusively through smartphones? So we came up with this idea of a phone. So you buy an off-the-shelf, in this case Samsung Galaxy S5 phone, and you download our app, and then you buy a USB cable, and make sure the USB cable is as small as possible because you want to limit the weight, and you plug it into a drone. This just happens to be the robot that we built, but it'll work with most drones. Then you can actually power the device using a smartphone. So I want to show you, this is Giuseppe Loiano's work, and show you the robot that he built, where this phone is actually taking pictures of everything it sees in the environment 30 times a second, calculating features in the environment, estimating distance to the features, and from that, estimating its position. So all the computation and all the sensing is done on board using the phone's camera, the phone's processor, and the phone's inertial measurement unit, which is basically a system of accelerometers and gyros that measure accelerations and angular accelerations. So this is in collaboration with Qualcomm, but you can see 3 meters per second autonomous flight, all planned by Giuseppe through his software. And of course, you can get it to whatever you want. And you can just imagine you can take the mother of all selfies if you position it wherever you want. So this gives us some hope that you can actually build really lightweight devices with off-the-shelf hardware. So it's inexpensive, lightweight, and also safe. The other S word I talked about was speed. So this is what we'd like to be able to do. This is actually being driven by an expert pilot. And imagine, again, responding to 911 calls and getting there and responding to things quickly, finding out where the bad guys are. We'd like to be able to do this autonomously. There's only one small segment of this, and I'll show you this in a minute, where the flight is autonomous. So this piece, so flying down the hallway, this is about 3-4 meters per second, maybe a little more than that. So we know how to do that autonomously. But navigating these bends at high speeds and going up and down the stairs, so these are things we're still working on, but that is something we'd like to do before this then becomes an effective tool that we might imagine using in search and rescue and first response. So finally, I'd like to talk a little bit about cooperative control, where we look at the problem of how to get all of these robots to collaborate and do something useful. And of course, once again, we're inspired by nature. So this is a picture with 500,000 to 1 million starlings off the coast of Denmark, and you can see them form this incredible patterns in the sky. To my knowledge, they don't use a whole lot of mathematics to do this, right? But mathematics is the tool that we have at our disposal. So it's a real challenge to be inspired by nature and then work with tools that we know to create these kinds of behaviors. Instead of trying to mimic them, what we've tried to do is instead understand some basic organizing principles that we believe allows us to accomplish these kinds of movements. It's not just about flight. You can see ants cooperatively carrying objects, and they carry this object back to their nest. They think it's food, and the reason they think it's food is because this plastic object we created is coated with the juice from fig, so they think it's food, and they carry it back to their nest. But this allows us also to study cooperation. This is actually an elastic disk. And so it allows us to see which ants are pulling. You can see on the top which ants are pushing at the bottom. You could also see which ants are not doing anything. They're just goofing off, and they're there for the ride. But it's really intriguing how these ants spontaneously form teams and are able to accomplish these incredibly complex tasks, at least from a robotics standpoint. These are very complex tasks. So again, the organizing principles is first, each ant, each bird acts independently. So we want robots to think about being completely autonomous, being self-contained. Second, we'd really like them to work with local information. There is no way in a room like this, if we have to make decisions, that we wait for consensus to emerge and do something as a group. Maybe that's what the government does today. That's why they don't do anything. But it's very hard to achieve that, right? So you really have to work based on what you know locally and then act based on that. The third idea is also fairly simple. This notion of anonymity. We want individuals to be agnostic to who their neighbors are. So if you think about a completely altruistic society of robots, then the robots shouldn't care who their neighbors are. We want them to collaborate and behave exactly the same way, independent of the specificity of who they're surrounded by. So we try to incorporate all of these elements into our software. You can see here that he's demonstrating the first idea, that this is Katie Power's work, where she's encoded these leader-follower behaviors into the robots. So the first robot is literally hijacked by David Pogue, and he's able to manipulate it. The other robots are basically responding to the neighbors. And they don't care that one of them has actually been lifted up by a human being and is moving it. They're just reacting to the position. So the simple idea here is that a single individual can actually manipulate, well, maybe not quite a swarm, but in principle a swarm. So the control computations that have to be done don't scale with the number of robots. It's just the same computations you'd have to do if you just had a single robot. The second idea is this, again, concept of anonymity, Matt Turpin's work. And here you could see that the robots have been asked to form a circular pattern. They know the pattern that they have to form, but again, they are agnostic to their specific neighbors. They're agnostic to even the number of robots in the team. So as long as they know where the pattern has to be formed and what the shape of the pattern is, they're able to find their place, adjust their spacing with respect to their neighbors. And now we're beginning to see something that might resemble the pattern formation that we saw in the Starlings. Admittedly, for a very simple circular pattern, but still doing them autonomously without worrying about the number of robots in the team. And then finally, you see some of these things put together where the pattern actually changes shape, starting with a rectangle, then into an ellipse, into a straight line, back into a circle. In all of these computations, a programmer is essentially telling the robots what patterns to form by giving the robots different shapes as a function of time. And the robots figure out which robot needs to be where in order to describe the shape, and they adapt to the commands. So you can see how these kinds of algorithms might be used now for 500,000 robots if we had them. And if there were a place we could do these kinds of experiments, these algorithms would scale to those large numbers. So I want to talk a little bit about why we're doing what we're doing besides creating these cool videos and publishing them on YouTube. And of course, everybody loves those. But ultimately, we're interested in solving some real problems. The first problem area that we're very excited about is agriculture. So if you look at the challenges facing society, I think you'll quickly come to the conclusion that water and food, and actually these challenges are related, are our number one challenge. The efficiency of almost all production systems in the world has gone up over time, but for food, it's actually going down for a variety of reasons. So one thing we're really interested in is trying to see how we can use robots to monitor and tend crops. And here's our robot flying in an apple orchard, carrying all kinds of sensors. And they're able to, in this environment, do fairly simple things. So on the bottom left, they're gathering infrared information. On the bottom right, they're building three-dimensional maps of apple trees. And in the center, they're computing an index called NDVI. So each of these pieces of information is useful in order to assess the health of a plant. So for instance, if you know something about the size of the plant, if you have a three-dimensional map, you can fly by that plant week to week and measure the state of growth, and you can estimate how healthy it is. If you look at this NDVI, the central thing, that essentially tells you something about the vigor of the plant. Something even more basic. Flying past these plants, we can count apples, and we can estimate the yield on the plants, and helps them plan for downstream picking, harvesting, and then shipping. Something quite basic with every manufacturing facility has, but farmers don't have. Another thing, and this is Karthik Mohta's work, we're working on is this notion of robot first responders. So imagine you have a 911 call from a building. You can imagine a swarm of robots equipped with cameras getting to the building and surrounding it long before search and rescue workers come to the scene, long before first responders, police officers come to the scene. And what we are really trying to do with these, and on the top left you see the operator interface, what the dispatcher might see before he or she even reacts to the 911 call. The robots surrounding the building, deciding who takes up what position around what ingress or egress point, all the time assimilating information and building a mosaic, as you see on the top right, and a three-dimensional map on the bottom. So now, if a police car were to drive up to the scene, they would be equipped with all this information before they even get there, and they would know what to do before they got there. This is a very important tool in operations where oftentimes speed of response is so critical. So this is not true just for outdoor operations, but also indoor operations. And I want to show you some experiments we did. This was about 5 years ago, after the Fukushima earthquake. This is in a town called Sendai, not too far from Fukushima, where our aerial robot is hitching a ride on one of our Japanese colleagues' ground robots. And by the way, the reason it hitches a ride is because our robots are programmed to be lazy. They burn a lot of power, so anytime they can ride on top of something else, they do. But you could see in this collapsed doorway, they quickly realized that the team cannot go through, so the aerial robot takes off, is able to cross over the bookshelf, see what's on the other side, all the time creating a three-dimensional map. This kind of information then can be made available to somebody who is standing outside the room, or outside the building, and providing just valuable information in terms of the structural integrity of the collapsed building, in terms of potential victims, and assessing the state of the building. So we, in this particular experiment, and again, this was 5 years ago, we were able to build three-dimensional maps, and this is three stories, 7th, 8th, and 9th floor of a 9-story building. So the map has, it's a 5-centimeter resolution map, and this took a long time to build. This experiment lasted about 2.5 hours. And that's one of the challenges of robotics. If I tell a search and rescue worker or first responder that I want you to give me 2.5 hours so that I go into this building and give you this wonderful map, nobody's going to give me that time, right? I'll be lucky if they give me 2.5 minutes or maybe 2.5 seconds. And that's where this idea of swarms comes in. We really want systems that can go in really quickly, collect the data, and by the time they come out, they've assimilated this information and built a three-dimensional map. And that's the kind of thing we're shooting for. So let me just conclude with a poster of an upcoming Warner Brothers movie called The Swarm. Actually, some of you might be old enough to actually remember this movie. Has anyone seen this? So if you've seen it, you probably know that you won't recommend it to your friends. It's actually a terrible movie. It's about killer bees that attack mankind and so on. But I love the poster because everything about this poster is true. The size is immeasurable. I hope I've convinced you the power is limitless. Even that last piece, its enemy is man, which is true. We have the technology, and we have to find a way to harness the technology and use it in a way that could be beneficial to society and to mankind. So even that part is true. So thank you very much.